Alright, so welcome back again. Now, what we learn how to do interrupts, but this time we won't use an input or output. We'll use the how is it called? The inside timer instead. And let me pause here for a second. Okay, just getting this picture out again here. We are going to use the interrupt clocks and of course the oscillators as well. So there's the first the PIC 18F252. Sorry about that. The PIC F18252. You can put two oscillator sources inside. For example, OSC1 clock 1. This one is only an input, so you can only put it in through. While this thing should have three, not three, should have four clocks from what I understand. I can see only like three of them. Oh no, there you go. We have T0 clock, okay, in RA4. We also have this one is the input of the frequency, so we don't really touch this one. You can see from the arrow as well. This one is the output, and it's also a clock. This one is T1 clock, so this one maybe it's not the output frequency, perhaps I'm not sure. And there should be another one. There should be a second clock in here, but I can't really see it. It's a little bit strange. But yeah, you should have three clocks. Maybe it's not on this diagram, maybe it's in another one. But basically what we're going to do, we are going to work with the second timer, the second clock, and we are going to use that second clock as an interrupt. Now, again, everything here is blank. The actual code is the same library, the same configurations like before. So let's get started with the definitions. See here, the first definition will be define set A trace about that trace A. Alright, and also as a hashtag define out pin port A bits dot R A 0. There you go. Now you may notice that we have only these two. We don't have port B anymore, and we don't have any bit B. And that's because we don't really need it. Again, we are using the internal clock, the internal timer to do the calculations here, to do the interrupt. So we don't really care about port B. We care only about port A, RA0, so we can actually get an output from it. Now the next step will be to set it to 0 to set the trace A to output. So let's go here, functions. So enter, void set up bracket void. Yeah, I think it's a semicolon in there. Now let's go down here, the setup function. So void set up bracket void bracket. There you go. Now we set everything to output, so trace A will be equal to 0, B 1 2 3 4 5 6 7. There you go, all of them are outputs. Let's also set the how is it called, the out pin equal to 0, make it a low. There you go. Alright. What did I misspell it? Oh yeah, I did. Out pin, there you go. And let's set all of them to digital signal. So ADC on 1 bits dot PCFG equal to 0B 011. Alright. Now this one is the basic setup and is the simplest part. Now. Another thing that we want to do, it's in here, Each has set up parameters, set up bracket semicolon. Okay, we initialize the setup as well. Now we actually need to do the interrupt. And if you think the interrupt from the last lesson was complicated, this is a little bit more complicated because, and I'll pop it up in a second. Is there a diagram for it? It's not on this page, which is a little bit annoying. Oh, there you go. There you go. Now, this is the timer. It is from the Microchip website, by the way. So you can see it, Microchip developer head. Now, this is how the timer interrupt works. Basically, you have a prescaler, which is the frequency divided by 4, and then this prescaler, it can be a ratio of 1 to 1, 1 to 4, 1 to 16, and 1 to 84. I thought there was a 1 to 8, and you'll notice that mistake when I'm doing the calculation because I honestly thought there was a 1 to 8, but I changed it to 16 because 16 is apparently the maximum. There's no 1 to 64 in there. And then there's a comparator, and then there's the postscaler. And the postscaler is 1 to 1, 1 to 2, 1 to 3, 1 to 4, and until 1 to 16. And then the interrupt happens. And basically the comparator will compare. So when the value of 255, which is the maximum, it's reached, then the interrupt will happen because TMR2 it's 8-bit as well. So it can count only from 0 to 255. If it was 16-bit, it will count from 0 to 65,280. Now, I know this sounds very complicated, but you'll understand soon when we actually do the calculations on paper that I showed you. But I will also show you the formulas as well. So, this is the first set of formulas, and the person here gives a nice example as well, because again, I need to do this research for myself, and he wrote it a lot nicer. Again, it's on the Microchip website, it's on their forum page, and the way that he explains it is, first of all, you want to find out the frequency desired, basically what frequency you want, and as I showed in the calculation, you basically do 1 over the desired time to find the desired frequency. Because what this does, it's basically lowering the frequency, making it slower. So it takes longer to count. The actual frequency input that goes inside the machine is the frequency of the oscillator that you plug in divided by 4. Again, seen from here, F oscillator divided by 4. That's the actual frequency that goes inside the prescaler. Alright, the time input, it will be 1 over the F input, and that one basically is the actual time that it takes to count. It's the actual delay without any prescale or postscale. For example, if prescale was 1 and postscale was 1, then 1 over F input will be the time that you'll get. And PR, it's basically to measure. This value needs to be between 0 and 255 to be working, and you do the time desired, the time that you want, divide by the T input that you find it from here, multiply by the prescale, multiply by the postscale. Okay? Alright. Now, you may wonder, well, what value should I put for prescale and what value should I put for the postscale? Because I don't know how to find this one out. And what value should I put for the frequency oscillator? Well, you can put any value you want on this one. It doesn't really matter. It's basically if you are obligated to use a specific one. For example, if your system runs at 6 megahertz, then you have to use 6 megahertz. So you have to use 6 megahertz divided by 4 in here. You know. So yeah. Now, prescaler and postscaler, what are they? Well, they have rated it as A and B nicely here from my university page here, because they also have their own formula that they give it to me for the timer setup. Basically, they say like the time desired, which is this one here, t2 int, it's equal with 4 multiplied by a, which is the post-scalar, multiplied by b, which is the prescalar, multiplied by pr2, which is the value that we're going to put in 0 and 255 plus 1 over the frequency of the oscillator. Again, I'm explaining to you here because you can see the formula a lot lesser from here compared to me recording from my phone. But you'll see that from the phone recording, I did actually calculate it and I did get the values, and you'll see what this PR2 means, because this one is the most confusing one of them. And yeah, and to find out this value, you can simply rearrange it and get this one here. You simply multiply the time desired by the frequency, and then you divide by 4 times A times B minus 1. Alright, and let me show here. So this one is A, this one is the post-scalar, and this one is B, which this one is the prescalar. And this is very confusing, and I think it's here as well in the diagram, isn't it? Yeah, prescalar, post-scalar. It's confusing to call A the post-scalar, which basically will be this one here, and B the prescalar. Anyway, so the post-scalar has only 4 values. It can be a ratio of 1 to 1, 1 to 4, 1 to 16, or 1 to 16, as seen here for the prescalar. It can be only 1 to 1, 1 to 4, 1 to 16, 1 to 64. Oh, I think maybe, yeah, it is the prescalar. Sorry, maybe he made like the lecture made a little bit of a mistake here. Never mind then. So yeah, this is the prescalar value. Now this one B is the postscalar values. And oh no, I put god, that means I put the wrong values in my paper when I did the recording as well. Sorry about that. You will ignore that please when I'm doing the calculation. Anyway, so the prescalar is 1, 2, 3, 4, 5 until 16. It's nice, it shows you what values you should put to get the number, but you can calculate it yourself as well, 0, 0, 0, that's simply 1. Next binary number, that will be 2. Next binary number, that will be 3, and so on until 16, until the maximum binary number. Alright. Now, if we go back to the example here that he gave us, what he did, it says, so say for example, you want 1k hertz timer from a 1 megahertz frequency oscillator. So it's telling us we want 1000. The time that we want will be 0.001 seconds. That will be 10 milliseconds, isn't it? I think so, or 1 millisecond. The input, it will do the 8 megahertz divided by 4. That will give him how is it called, 2 megahertz. Then the time input will do 1 over that 2 megahertz, and now it's in microseconds, I think. And then he decided, okay, let's do some guesswork, because we need to do some guesswork. Let's say the prescalar will be a 4, it will be a 1 to 4, and the postscalar will be a 1 to 1. He does the calculation here. This is the desired time, which is 1 millisecond. The 5 microseconds multiplied by 4 multiplied by 1, that gives for the PR 500. But again, what you need to remember is that it's an 8-bit. It has to be between 0 and 255, and that's as he mentions here as well. So now he changed it. He made the postscalar 1 to 2, so basically just halving this in 250, and this one fits in, meaning that the settings that you need to program in the program for the prescalar and postscalar will be a 1 to 4 for the prescalar, so that will be a 0, 1, and a 1 to 2, which is this one, and for the postscalar will be 0.001. Right? I'll stop the recording here. You'll see me doing a calculation as well. We'll calculate how to get 15 milliseconds with a frequency of 12 megahertz. and I'll see you after that.
Okay, so you have seen kind of a nicer layout for this diagram, and also the pre-scale and post-scale as well. Let me just pop them up on the computer so I can have them too and see them as well. There you go. Now let's actually go through one of these problems and try to solve them. So let's see. We will try to calculate the time delay because that's usually what you care about. You don't really care about the frequency that you want to get because it's not that important. So let's say that I want, let's write it here actually, and I'm using the math so I can actually tell if you can see on the camera or not. So let's write here what we want. Well, we want a 15 milliseconds delay at 12 megahertz. It should be possible, I think. We'll see in a second anyway. And we are going to use the PR2, basically the second timer, and we know that the second timer it's an 8-bit timer, a bit, which means that the PR2 should be between 0 and 255. Sorry about that, this is not really that important for now. So we will use the simple formula, which is this one here, and at the beginning it's guesswork, to be honest. Or you can actually use this one here as well, which is the longer one. So let's start with this one, the longer one. What time we desire? Well, but we don't know the desired frequency yet, so that's fine. The input, frequency of the input. Okay, so let's calculate it in this way. So let's start with the time desired. So, and we need to start with the frequency desired as well. Let me get the calculator. There you go. The way we calculate the frequency that we want is quite simple, because to find out the time that we want, we do 1 over the frequency. So if you want to find out the frequency that we want, we just do 1 over that time. So we want 15 milliseconds times 10 to the minus 3. So the frequency that we want is 66.67 hertz. So 66.67 hertz. Let's test that. So if I do 1 over 66.67, it should give me, yeah, it's about 15 milliseconds. There you go, 14.9999. all right, so this will be the desired. So F this red will be equal with 66.67 hertz. Now the time desired, we already know that one, it's 15 milliseconds. Now the frequency input, F input, will be equal with FOSC, which is the frequency of the oscilloscope, divided by 4. And we say that it will be at 12 megahertz. So then we can just write it 12 times 10 to the 6 divided by 4. And that one will give us 3 times 10 to the 6th hertz. There you go. So now we have the F input, and now we just need the time input. And T input will simply be equal with 1 over F input. And F input is 3 times 10 to the 6th, and that one will be equal with, so that'll be 1 over 3 times 10 to the 6th, 333.33 microseconds. 333.33 microseconds. There you go. So we found those values. Let me push this one a bit higher up. There you go. Now what we need to do is to calculate the PR value. So PR2, it's equal with the time desired, which is 15 milliseconds, divided by the input, which is 333.33, micro multiplied by the prescaler, and let's say we'll put a prescaler of, let's put it of 8, why not, and then multiply by the postscaler, and let's say postscaler will be 10. Okay, and that will be equal with, because when applying this type of formula I also need to do some guesswork, so times 10 to the minus 3 over 333.33 times 10 to the minus 9 multiplied by 8 multiplied by 10. Okay, and that one it's 562.5. Close enough, but it's still too far. So then let's do it again. Equal 15 milliseconds divided by 333.33 micro multiplied by 8. This time let's make it a bit lower. Let's put it as a 9. That will be equal with. So instead of 10, we'll put it as a 9. And oh no, it went up, 625. So instead, let's make it 11 then, multiplied by 11. Remember, this one will go up to 16. And now it's, oh no, wait, it's very far off. Yeah, sorry about that. Because we need 255, and this is in the 500s. So 8, it's obviously not going to be enough. So you change that up to 10. So from the postscaler, we know this one can be either 1, 4, or 16. So, okay, sorry, I don't know why I put 8 in here. So let's try with 16 then. And with 16, that's 281, which is better. So let's put 16 times 10. Let's try with 12. 12 is 233, so 234.4, which is close. What if I put 11? 255.68. Now this is a little bit above. Okay, so let's try with 9. And 9 give us 312. So 10 give us 281, which is above as well. Okay, let's try 8. 300, okay. 12 maybe? Yeah, 12 it was the one that we tried. Let's try 13. There you go. And 13 will give us 216.35. Okay, I hope you saw the calculations that I did in here. Now, we have these two values, and we can keep going. We can say like 14, because this should fit as well. Like to be 215 will be 187.5, and the last one will be 16. That will be 175.8. And all of these are correct answers because all of these are between 0 and 255. But now, how do we test if this is the correct answer? Well, we can apply another formula, and I'll write it quickly here because I don't want to start on a new page. And the formula will be the following. T int basically is the time desired, or the time that we want to have, or the time that we'll get. It's equal with 4 times A times B, postscaler, prescaler, times P R2, which are these values here, plus 1, close bracket, all over the frequency f. Okay, so we can rewrite this one as 4 times. In this example here, we use the 16 for the postscaler, so 16 times, and we use 12 for the prescaler, 12. And then with the answer that we got, times PR, which is 234.4 plus 1, all divided by the frequency, which we said was 12 megahertz. 12 times 10 to the 6th. That will be equal with, so let's see here, 4 times 16 times 12 times bracket 234.4 plus 1, close the bracket, 12 times 10 to the 6th, There you go, and that one gives us 15.0. Let's round it up to 0.7. There you go. It is 15 seconds, but it's not the perfect 15 seconds, and I don't think you'll ever get the perfect one. Now, if you want, we can check the. Sorry, my screen went off. We can check the other ones as well. So this one was 15.07 milliseconds. Let's try the other ones. So the next one was 13, and the PR2 it's equal with 216.35 equal with, and this one is a bit far off. I mean, it still runs up to the same value. Okay, 0.7 ms, and the higher we go, I think the worse it will get. So let's say the next one is 200. It was at 14, and oh no, did I calculate that one wrong? It's actually a better result. Let's have the other one. 87.5. Then this one will be for the 15. 0.8. Yeah. So I would say this one here is the best value. So we'll use this value. And that value, we got it because we had the post scalar, we had A equal to 16, and we had B equal to 12. And writing this in binary language, in code language, then A, it will either be 10 or 11, and B will be equal with 1011. There you go. Now, why do I show you the calculation in here? And I know it's a little bit messy, but you get the idea, because most of the time it's just guesswork. You will have a frequency, you will have a desired time that you want to have, for example 15 milliseconds, and then you need to make sure if it's in 8-bit it will be between 0 and 255, but some of them have 16 bits as well, and those are more interesting, because if it is 16 it should be between 0 and, let me do this quickly, so 12555 times 2, 1, 2, 3, 4, 5, 6, 7, 8. Alright, then it should be between 0 and 65280,000, which in milliseconds that can be any number really. So you don't need to worry too much about this one. Again, this is in 16 bits. We don't work in 16 bits, we work in 8 bits for now on this PIC. Alright, so I hope you saw everything here. I hope you understand. Again, just going over the steps. First step is frequency desired. How do we calculate that? You put 1 over the time that you want, which was 15 milliseconds. So there you go. It gives you the frequency that you desire, the frequency that you want. Then for the frequency input, you use the frequency of the oscillator, you know, the one that you actually plug in the timer, and you divide that one by 4, and then it gives you the frequency in hertz here. Next step, it's you do the time input, you do 1 over this frequency here, that gives you milliseconds, and then it gives you the value of PR2 when you actually calculate it like this. Alright, when you put the time input multiplied by the prescaler multiplied by the postscaler, it gives you this value here, and you repeat so until you get a number between 0 and 255 if it's 8-bit. If it's 16-bit, you saw that goes between 0 and 65 280,000. Alright, now we'll go back to actually programming, and again I want to mention that, yeah, I don't know how to set this in MPLAB, because if I set the instructions frequency, then it won't be an accurate representation. It won't say it takes 15 milliseconds or 10 milliseconds or whatever the value was. It will just tell you, oh, okay, it took only like I don't know, 2 milliseconds or something like that. And we'll see now when we actually do the programming. But again, remember, don't trust MPLAB when checking for the time that it takes to do the interrupt. Do the simulation, test if the interrupt actually occurs automatically after a period of time, but remember, this here is the actual period of time that it takes. Now what it tells you on MPLAB. Alright, I'll pause the video here.
Alright, now that you actually saw the recording and how to calculate it, and hoping that you understand, even with my writing, how to do it, and understand that's quite simple, isn't really that difficult. And if you want, you can do some practice as well, see if you get the answers, because it's actually easy to check too. So let's start actually putting some code in here. So from our calculations, we got for A, which is, again, don't follow what I wrote in the paper, it is the prescaler. For A, we got a 1 to 16. So how do we write this? Well, we need to do it from the setup. So let me press 2 enters, put a comment here, interrupt set up, put out the ones, and the way we do this is we say t2 con bits dot, there you go, it gives us t2ckps, sorry, tab, come on, there you go, equal to 1 there you go. And this one is the prescaler. I'll get this one out again, just a second, there you go. So it's called T2 CKPS that we just wrote. We wrote it as a binary 1 meaning it will be a 1 to 16. We can also write it as a 1 0. It won't make a difference to still be 1 to 16. But there you go. That's how we actually write it. Now what we need to add is the postscaler, which will be this one here, the TOUTPS. And we got the number 12, which, as we wrote to the paper, the binary for that will be 1011. So let's press here enter, t2 con bits dot there you go, tps equal to 1011. There you go, nice and easy. Now let's press enter. This is another enter here, and now let's actually set up the interrupt. So you write it IP R1 bits, basically telling the interrupt with IP R1 bits dot there you go, timer 2 equal to 1, basically saying enabled. There you go. Actually, let me write down here as well what this one is. This one is value of A, oops, I forgot the comment, value of A bracket keys scalar 1 to 16. Let me go beneath, tap a couple of times, comment again, value of B bracket post scalar, and this one was a ratio of 1 to 12. There you go. So now you can understand what it is. We'll write this one's different. You don't need to remember these two names. I'll show you an easier way to actually do this entire setup. And another one is we'll put it as a timer. Basically, what we did this here, it's enable timer 2 high DOTT. Basically, because there are two timers that we can use in here, as you saw from the autofill. So this timer will be at a higher priority than the first timer. Just saying that the program You don't have to do this because we don't have any other timers or any other interrupts of timers, so it won't really make that much of a difference. And now we do here PIE1 bits dot TMR2IE, okay, basically setting the flag equal to 1. What this does, it's again comments enable timer to interrupt. So basically what this does is saying the program to create timer 2 as an interrupt, to allow to be an interrupt. Alright, and this is not the last step. The last step will be here, which will be, if you remember, it will be int con equal to 0b, and this time it will be 1 1 0 0, because we are not using the RB0, we are not using an input as an interrupt, and again another 4 zeros, 1 2 3 4, semicolon close. Again, let me get out Google. There you go. Let's go back to the diagram that we used last time. Just wait for it to load. There you go. So yeah, again, what we did, put the 1 for this one, enables all interrupts, and this one here on bit 6, this one is the EE interrupt. So this one is basically the timer interrupt. I think it mentions here interrupt may require program because yeah, time for its operation is complete, allowing the program to do other things instead of holding, and so on and so on. Yeah, so this one is for the timer interrupt basically. Alright, now we still have no actual interrupt because we need to write it here. There you go, interrupt if used. So let's actually start writing the interrupt. Alright. Oh no, wait, I forgot to do another important step. You actually need to start the timer. No, how could I have forgotten something so important? Alright. So, oh no, and I forgot to one in here as well. There you go, now it's actually all digital outputs. Alright, so T2 con bits dot TMR2 on equal 1, semicolon, and what this does is start timer 2. You actually need to tell the program to start the timer. It doesn't start it instantly when the program starts. Again, so you can play more around it. Maybe you want the timer to start after an interrupt, or you want the timer to start after a certain order of the program, you know, like around step 5 or 7 in the program, then you want the timer to start. But we want to start right away, so we put it on the setup. There you go. Again, that was a big one that if you missed, there will be an error. Now let's write the interrupt. So void space low interrupt bracket high int bracket void close bracket squiggly line enter if PIE1 bits dot TMR2IE, there you go, and 0 0. So if that one is a 1 and PIR1 bits dot TMR2IF, which is the IF is the flag, and this is a 1, then it will execute the program. Then it will execute the interrupt. There you go. So then what we want to do? Well, we want to do a PIR1 bits dot TMR2IF equal to 0. And basically what this one does, it will reset the flag, so it's important for you to have this. And then the next one will be out pin equal to squiggly line out pin, basically making the opposite, making it from a 0 to 1 and 1 to 0. All right. And I think I need to put the return as well, so enter here return. There you go. Alright, so this is the interrupt. So I don't know if you notice TMR2IE is here as well, and this one is the flag, so it's nowhere to be found in here. But basically what it does is when this condition is true and when this one is true, so basically when both of them are ones, let's call it that, then it will interrupt, do the interrupt. Basically, to cut it simply, okay, basically what the program is telling it, it's that, okay, count from 0 to 255. When it reaches 255, trigger the flag, and then the flag is triggered and the interrupt happens. If it didn't reach 255 yet, then don't trigger the flag. That's it. It's that simple. Alright. Now if you run the program, there shouldn't be any errors, hopefully. Let me check something here as well. No, it doesn't mention anything good about the flags here. We'll look into this in a second. There you go, the program is built successfully. Analog in. What? Analog in, why is it that like that? 0P000 PCFG. These ones are all zeros. How strange. Let me get rid of this one first, actually. Delete. So the timer, this one is 0. This one is, let me reset it. So 1, 2, 3, 4, 5, 6, 7. Okay, that's the correct number. And then ATC on 1 bits. ATC on 1 bits dot PCFG equal with 0 B 0 1 1 1. Let me run it again. There you go, now it's a digital output. That was so strange. I don't know why was it an analog input for a second there. And yeah, it's a digital output. We simply can't change this value here. Wait a second, why did it not stop yet? Let's pause it for a second. Yeah. Oh, I know why. There you go. I think it. Yeah, I did change it. Okay. Let's reset it. Sorry about that. I forgot to put the breaking point. I was just waiting for like the program to stop. All right. There goes it again. There goes stop now. Stopwatch. There you go. See, it took 2.7 milliseconds to do this, and it's running at. I don't think you can see it yet there on the screen, but it's running on 6 frequency. Actually, let me stop and I'll change that to what we use 12 megahertz. Okay, so properties, there you go, simulation. Let's put here 12, like in the program that we did, in the calculation that we did. Let's add the program. There you go, it's running. It stopped. Stopwatch did that after 1.35 milliseconds, which it's wrong. It should have stopped at 15 milliseconds. But again, I don't know why MPLAB does that. I don't know why it doesn't like the way I put the instructions in, anything like that. But yeah, I can't do anything about it. R8 0. Now when I press next, there you go. It changed to 1. The program again runs for about 1.367 milliseconds, and it stopped again. It just got interrupted. And there you go. It's working perfectly. Now, I don't really have a method to show you that it actually does interrupt. I need to put here a line of code. Uh, what can I put in here? I don't have the delay option. What is it? Is it NOP? The one that does like one step and then it stops? No, it doesn't work like that. But anyway, the idea is that the interrupt works. Basically, it lasts for 136 after 136.53 seconds of running the program, it will stop. And I can prove you that this time can be different. If I simply change this one to a 1 to 12 ratio, which is a big difference, so if I make it 0, 0 and run it, there you go, go to the stopwatch, it took only 87.75 microseconds to actually execute the program. 85.33 microseconds now. See? There you go. So the pre-scale, it does make a difference in time, and it does make quite a big difference. You can see it in MPLAB, but it just doesn't measure calculations. And that's why I don't really like simulations, or much I prefer to use the actual physical microchip or microcontroller, because then I can actually plug it in something and measure the time it takes for it to like stop the program. And yeah, but I can't do anything about it, so for now we need to satisfy with MPLAB. But again, remember that from what I showed you how it goes and how it works. I showed you that it actually works. RA changes from 0 to 1, 0 to 1. So it does the interrupt. It does run through the while loop. So yeah. But another way you can write this, which I might rather prefer than this, um, is the following. So let me pause it here. Let me get back to Google. It's using this. And you may think it's complicated, but it's not. It's quite simple. So you see, T2 con equal to 1, 2, 3, 4, 5, 6, 7 with 7 bits. These first 4 ones are the post scalar that we used at that b value that goes from 0 to 0 to 1, 1, 1, 1 that we know. This one here is the pre-scalar that goes from 1 to 1 to 1 to 16, because again 64 doesn't exist now. And this one here is to turn on and off the timer too, so we can actually shorten 3 lines of codes, and we don't need to remember the actual names, because we can simply write it as, let me like put it up actually on the side here so I can see it. We can get rid of this one here. We can get rid of these two here. And we can simply write it as T2 con equal to 0b. So what we wanted for the first one, we wanted for 1011, which is a 12. 1011. This one is the post scalar. Now we are telling the program if the timer 2 will go on or off right away. It will say will go on right away. So this is a 1. And then I will do the pre-scalar value. And it can, we put an 11 before, but let's put a 110 this time to show that it doesn't make any difference. Even though on this one here it says it's 1 to 64, it's actually 1 to 16, because I think they use a different microchip for this one. So, oh, it doesn't like that very much. Let me put this here. Do you like it now? You say don't like it? Okay. Let me put capital letters then. There you go. Do you like it now? Yeah, now you like it. Okay. There you go. The program ran successfully. There's no bug. And look at that. The interrupt worked. And look at that. It took. Oh no! Wait, it's a different one. We used like 6 megahertz. Let me put it to 6 megahertz to show it's actually the same one. When it was 6 megahertz, it was this one here. It was. Oh no, wait, it wasn't. That's interesting. That's very interesting, actually. Hmm. Let's check a little bit more in depth. Okay, so this one was for a 1 0. What if I put a 1 1? Oh no, wait, I realized that you actually didn't see any of that. You saw only the top part here. Sorry about that. Let me just drag this one a bit higher. There you go. You should see that all of them. Okay, so this one was our first one. Then this one is when we change it to 12 megahertz and we change it to like 0 something. And these ones are the new ones. So let's see. Yeah, it didn't really change anything. It's actually the same number. So I was right then. Okay, does make a difference. I thought it would be something like this one here, but I guess not. Right, where was it? Here it is. Right, and that's how we do a timer interrupt. Basically, no need of an input or output to do the interrupt. The microchip itself will just count until the interrupt appears after a certain amount of time. All right. Uh, Thanks for watching, and I'll see you in the next one then. Bye.